300 million years ago. Shallow prehistoric oceans hosted immense predatory biomass. Colossal marine organisms required continuous, massive caloric consumption. Dunkleosteus possessed massive armored plating across the cranial region. The bony armor exhibited ultra-detailed textures, jagged edges, and severe battle scars. Thrusting such immense body mass through dense water columns demanded staggering kinetic energy. Water resistance restricted Dunkleosteus to deliberate, heavy, and physically exhausting movements. Biological survival necessitated the constant aggressive pursuit of large prey. Similarly, Helicoprion utilized a specialized tooth whorl to sever and process muscular prey. The unique spiral jaw structure required vast and continuous cardiovascular output. Helicoprion patrolled sunlit pelagic zones, competing directly with other massive predators. Predation at the massive scale mandated high oxygen saturation and abundant resources. However, beneath the turbulent, hyper-competitive upper oceanic layers, a radical evolutionary divergence occurred. Far from the sunlit slaughter, the abyssal mesopelagic zone offered profound biological isolation. Here, Vampyroteuthis infernalis abandoned the violent biomechanical arms race entirely. Instead of developing massive jaw structures or heavy dermal plating, Vampyroteuthis infernalis descended. The vertical descent led into hostile environments where ambient light failed completely. Down in the abyss, drifting marine snow replaced fast, active prey species. Suspended microscopic particulates filled the frigid, high-pressure water column. Densely, a common anatomical misconception labels ancient surviving lineages as evolutionarily stagnant. Reality proves the exact opposite. The anatomical structure of Vampyroteuthis infernalis represents a state of absolute metabolic optimization. Apex giants like Dunkleosteus relied entirely on brute force and extreme caloric intake. Consequently, Dunkleosteus faced inherent vulnerability to sudden planetary ecological collapses. Conversely, Vampyroteuthis infernalis engineered a permanent deep-sea physiological escape route. Fossil records confirm the anatomy of Vampyroteuthis infernalis remains virtually unchanged over millennia. 300 million years of morphological stasis indicates unparalleled biomechanical perfection. Vampyroteuthis infernalis simply bypassed the devastating extinction events that entirely eradicated Dunkleosteus. The survival strategy involved permanently entering the suffocating oxygen minimum layer. The specific ocean depth features crushing physical pressure and near freezing temperatures. Only faint volumetric rays occasionally pierce the absolute upper boundaries of the zone. Within the freezing, hostile darkness, Vampyroteuthis occupying the oxygen minimum layer required radical physiological modifications. Oxygen saturation here drops below 5%. Most cephalopod species rapidly asphyxiate within such an extreme environment. Vampyroteuthis infernalis survived by evolving highly specialized hemocyanin proteins. Hemocyanin efficiently binds trace oxygen molecules extracted from the surrounding frigid water. Consequently, Vampyroteuthis infernalis maintains the lowest specific metabolic rate of any known cephalopod. Surviving alongside massive, high-energy predators like Xiphactinus, a prehistoric fish, necessitated this exact metabolic suppression. While Xiphactinus burned massive caloric reserves hunting fast prey, Vampyroteuthis infernalis simply drifted. Passive drifting requires virtually zero kinetic energy. The extreme hydrostatic pressure at 3,000 feet below sea level compresses biological gases. Ancient predators navigating vertical water columns risked catastrophic physical trauma. Conversely, Vampyroteuthis infernalis utilizes statocysts to maintain perfect neutral buoyancy. The gelatinous tissue of Vampyroteuthis infernalis perfectly matches the density of the surrounding abyssal water. Such precise density matching completely negates the massive energy expenditure associated with continuous swimming. The anatomy of Vampyroteuthis infernalis features extensive webbing, connecting 8 arms. Rough, ultra-detailed textures cover the inner surface of the webbing. The deep red biological textures blend perfectly into the absolute darkness. Instead of hunting, Vampyroteuthis infernalis extends too specialized. The filaments function as biological nets, capturing drifting marine snow. Marine snow consists of descending organic matter, including decaying tissue, feces, and microscopic particulates. Vampyroteuthis infernalis passively gathers the detritus matrix. Sticky cells along the filaments bind the organic particulates into concentrated, edible clusters. Vampyroteuthis infernalis then wipes the concentrated detritus directly into a central beak. Passive feeding eliminated the need for aggressive cardiovascular systems or heavy muscular density. Occasional parasitic scarring marks the soft tissue of Vampyroteuthis infernalis, revealing survival against abyssal parasites. However, physical combat remains entirely obsolete within the behavioral repertoire of Vampyroteuthis infernalis. Slow, deliberate physiological processes mirror the absolute stillness of the abyss. Vampyroteuthis infernalis achieved true ecological immortality through profound biological minimalism. Biological minimalism does not equate to absolute vulnerability within the abyssal ecosystem. Predatory threats still navigate the deep ocean currents, seeking vulnerable biomass. Ancient shallow water cephalopods developed dark melanin-based ink to obscure physical escapes. Releasing dark ink within the pitch-black mesopelagic zone provides zero tactical advantage. Consequently, Vampyroteuthis infernalis engineered a completely different, highly luminous biochemical deterrent. Bioluminescent photophores cover the entire outer biological surface of the deep-sea cephalopod. When threatened, the ancient and mysterious Vampyroteuthis infernalis avoids rapid. Instead, Vampyroteuthis infernalis executes a defensive anatomical inversion, termed the pineapple posture. The webbed arms retract upward, completely enveloping the vulnerable cranial region. The inversion exposes rows of fleshy, sharp-looking cirri lining the inner webbing. The cirri present a false physical threat, mimicking heavily armored defensive spikes. Simultaneously, specialized organs located at the arm tips discharge a luminous bioluminescent matrix. The glowing mucus secretion explodes into a dazzling cloud of luminescent blue orbs. The brilliant biochemical display visually overloads and disorients, approaching abyssal predators. During the resulting confusion, Vampyroteuthis infernalis utilizes efficient jet propulsion to retreat. Vampyroteuthis infernalis slips away into the darkness. Such specialized adaptations allowed Vampyroteuthis infernalis to endure, while apex giants perished. Massive predators like Predatory dominated ancient oceans, using pure mechanical superiority. However, sudden environmental shifts collapsed the high-energy food chains, supporting Predatory. Meanwhile, Vampyroteuthis infernalis remained utterly insulated within the deep, freezing ocean layers. 300 million years of fossil records prove the ultimate superiority of adaptation. Vampyroteuthis infernalis outlasted every dominant marine giant by simply requiring less energy. The abyssal zone provided the ultimate sanctuary against planetary ecological devastation. Vampyroteuthis infernalis remains an undisputed biomechanical master of the ancient deep ocean. If the deep-sea biomechanics and prehistoric biology provided valuable insight, please like the video. Subscribe to the channel for more authoritative explorations of ancient and modern ecosystems.